So our next presenter is Sachin Kumar. Sachin Kumar is working as a senior engineer at ARM. Sachin has been working at ARM since 2020. He has almost entirely worked on formal verification, both in control and data path handling in last 6 years. He has presented 2 technical papers on formal till now. So Sachin, please go ahead. Thanks.
Thank you. Hello. Thank you, Girish. So my name is Sachin. With me, other co-author is Rajesh. So we are from ARM and presenting on formal effective deadlock verification methodologies for the interconnect design. So in agenda, there are 2 parts. So in first part, I talk about the design, that is interconnect, and its microarchitectures. Then verification scope for the deadlock and reason why formal verification is used for the deadlock verification. Then as part of setup, I will detail on different formal checkers. In second part, I talk about different formal methods like bug hunting and with examples on helper covers and conversion of property to safety and case splits. And then share statistics of results across these methods, then summarize the presentation with the summary slide. So interconnect, it is a network. It can be mesh or ring. It contains nodes and components. Components can be shared slices, CPUs, any external components. So the node is the integral important element in the interconnect. So component send messages to the different components. The messages can be data, response, request. The node, based on the number of nodes, interconnect can be configured into different topologies, like one node, which contains one instance of the node, two, and four node, 4 instances of the node. Each node is connected by a wire. So the node can have 0 number of components attached to it or more than 0. It depends on the configuration. So these components attached to these nodes have a source and sink port. So the source port is used to send messages to the interconnect and sink port for accepting messages from the interconnect. Also, this component have multiple channels. Across these channels, source and sink ports are present. When a component wants to send a message to the interconnect, node chooses the optimum path based on the traffic in the interconnect and then send a message on either of the direction, clockwise or anti-clockwise direction. So about microarchitecture, so there exists arbitration on each node across the interconnect. So every message from the source, like from the component, has a routing information. Means it contains the destination address. Node uses the destination address and compares with the source address. If it is matching, then the message is targeted to the same node where the source is present. If it is destined to the different node, then the node arbitrates the message for the ring access. Once the message is in the ring, then the message is arbitrated at the sink port at the destination component. So each node have starvation mechanisms. For example, denial of service kind of starvation mechanism. It is used to prevent harmonic sequence of transactions from some sources which blocks the forward progress on other sources. Also, interconnect responsible for making sure fairness among all the sources. So on the bandwidth of the interconnect. So depending on the number of nodes and components and their placement and other parameters, interconnect can be configurable large number of times. So this is the one challenging point in verification covering the huge amount of design state space. So as part of verification scope for the deadlock, so the presentation is mainly talking mainly on the deadlock verification. So the verification scope is there is no deadlocks. For example, the message is not stuck in the skid buffer or the FIFO present in the interconnect, or the message is not respinning forever in the interconnect. These are the common deadlocks which designers prioritize for fixing the deadlocks. Other deadlocks like denial of service kind of bugs. Also in interconnect, the message flow can be out of order. But we need to verify the integrity of the message. There is no corruption or there is no loss in the message. For example, in this case, there are two balls in the ring. So they have the destination address. They reach the destination node where the destination node is unable to sync the message, and these two balls are bounced back to the ring. This process continues for the infinite cycle. So this is a classic example for the deadlock. So example for the denial of service kind of deadlock. So in this case, there are two sources, source 0 and source 1 on node 2. Both sources have a valid message at the same time. But without anti-starvation mechanism, let's say, node 2 is accepting messages from the source 0. So thereby the forward progress on the source 1 is blocked, which results into a denial of service kind of deadlock for the source 1. So in general, in reality, in the chip, this kind of bugs may not occur. So formal can find this kind of bugs, and we need to fix these bugs as part of the anti-starvation mechanism. So the reason why formal verification is used, so the simulation is less efficient in terms of stimulus. So where right stimulus need to be applied. Sometimes the test case passes when the timeout is increased. And in simulation, there is no direct way to represent the liveness checking. So whereas in formal, we can make use of SVA construct, S eventually, and write a liveness property. Also, every year, the complexity of interconnect is getting complex because the number of components are getting increased, and update on the microarchitecture features, and these microarchitectures are big, and they are present across all the channels. So interconnect can have more than 4, 5, 6, depending on the design number of channels. So verifying deadlock verification across all these channels in one setup, in formal, it is more complex and it is challenging. Properties may not converge. So formal provides a way to black box, so we can verify deadlock verification on one channel by black boxing other channel. Also, if there is any dependency between two channels or any complex logic present in the channel, we can replace it by means of a cut point and a constraint. So what is liveness? Liveness property for the formal means good things eventually happen. A typical liveness property in interconnect is a source message from the node is eventually accepted in the interconnect. If not, formal gives a counterexample. That counterexample contains two parts. One is the fixed sequence followed by the loop. So now as a formal verification engineer, we just need to find out reason why design is unable to come out of this loop. That gives the reason for the failure. So now, as part of the setup, we have different checkers present, like interface liveness checks. These properties are easy to write. Like they are straightforward at the interface level. So these properties mainly target denial of service kind of deadlocks. So since it is simple, it is the interface level, the huge amount of complex logic is present in the COI, in the cone of influence of these properties. So formal saturates after days of run using the right amount of LSF resources. So second type of property is forward progress checks. So here the property checks the life cycle of the message. So interconnect must make forward progress or must sync the message within the life cycle of the source message. So these properties can be in line with the feature of the design, or it can be converted liveness to safety properties. So the third property is formal model end-to-end symbolic liveness checks. So since it is symbolic, so there exists some kind of modeling logic to represent the packet, the message flow from the source to the destination. So this property verifies the symbolic message which is tagged eventually reaches the destination. This property can verify complete verification scope. So the next property is over-constrained deadlock checks. So this is a special checker that we implement based on the number of bugs, deadlock bugs that is missed in the formal flow. So in formal, the nature is, it is like iterative in terms of debugging counterexample. So first counterexample that we find is related to the denial of service kind of deadlocks. It is not what we wanted to recreate. So which requires some kind of over constraint to reproduce that interested deadlock bug which is missed. So that's why we write the special checkers to recreate those bugs. For example, if source there is no messages are driven from the source, interconnect should be eventually empty. So now, in second part, as part of formal setup, the formal verification is run at the block level of the interconnect. We have removed the components and mimic the behavior of the source and sink port by means of a interface by adding constraints into the interface, source and sink. So abstraction is done at these two stages. One during the compilation and elaboration, like interconnect has FIFOs and counters used in this anti-starvation and different features. So those we work with the designer during the feature development and inform them we want the minimum value which is safe in the formal, which can be safe in the formal verification flow. In the second stage, the abstraction is done before running formal verification using the formaltical commands. So, so divide and conquer approach, as I mentioned, it is a black box approach. We can run formal verification on one channel at a time by black boxing other channels. So thereby we can reduce a lot of complexity and the proof in the what we achieve in the formal can be more compared to all the channels in one setup. So now, based on our experience over the year, we propose 3 methods. First one is guided bug hunting, which can help in finding bugs much more and in several factors quicker than the conventional classic formal. So second method is converting property from liveness to safety and case split based assume guarantee. These two methods are require more effort but good in the long term formal verification flow. So in the classic formal, the nature is like exhaustive, like a breadth first search. It verifies the state space cycle by cycle. So in classic formal, it has a bug hunting, which is like automated. We don't need expertise for that. So the bugs are found at the shallow depth, mostly the denial of service kind of bugs. They lack finding true deadlocks because of the lack of deep state space exploration. So we missed some number of deadlock bugs in the formal flow. So those bugs are eventually reproduced by working on writing new properties, that is over constraint deadlock checkers, spending more time because the bug take time to hit in interconnect. So like 1 day, 2 days. So we need to run the property until it is hit or until it is saturated. So guided bug hunting, where we can configure the initial state for the hunting using the formal model end-to-end checker or any checker which we think it is close to the states of the what state we configure. So in general bug hunting, it is like a black box. So take any tool, it uses from the research state, for example, it uses some internal way to jump to the some random state, for example, simulation engine, then verifies some time or some depth around that jumped state, then iterative jumps to some other new state and continues. So we have no idea what state space is explored. So it is like less control on the verification on the inside of what is happening from the coverage point of view. So we sign off based on the properties if it is saturating and there is no change in the depth, no new counterexample, no new properties are getting proven. So we think that the formal flow, this verification is completely saturated, then we close that particular configuration. Whereas in guided bug hunting, we need to discover helper covers to represent the deep state space interested design activity, and first we need to prove them. So then in the second stage, we need to run the formal model end-to-end checker, which it is the depth or the design activity which is covered. It is like an initial state for the property which we are running. So it is a hunting from that state. So some of the helper covers, like how to discover helper covers. So understand the proof of the target assertion which we want to run as part of the bug hunting. Write a cover which is close to the target property. For example, counter some conditions or some based on the feature understanding we can write. with good understanding of the microarchitecture, it is easy to and straightforward to write a rare design state activity using cover. So like for example, write a cover for like possible starvations. So to test the starvation logic is verified, is like bug free. So some of the covers which helped in reproducing some bugs which missed in the formal flow are source is not idle for some cycles and source is idle for some cycles. Then message, the packet enters the ring and after some cycles message is seen at the destination. And the starvation counter which is used in the counter used in the any feature like a starvation counter reaches a threshold value and after some time it becomes empty. It becomes 0. So it requires some of the helper covers require some modeling logic, but to start with we can use design inline properties, but we need to be smart in terms of checking the health of the formal run, because with less resources are given, if there are more number of covers, the more number of properties, the hunting or proof around these properties might not be more efficient, might not have utilized the sources for the full runtime. So we need to make sure LSF resources are given correctly as per the requirement, that is actually based on the helper covers and the target assertions. So the second method, it is converting liveness to safety. So in general, formal struggles for a full proof on liveness property, but it works better with the safety properties. So the meaning of liveness is good things eventually happen. So the safety means there is no bad things in the design. So in Interconnect, it has a feature like quality of service and bandwidth. It is to make sure each source has a equal bandwidth and the message is sunk before the within some finite cycles. So with that in mind, we can convert the property into liveness property into a safety property. So how we can do that? So we spend good amount of time because we need to go through a number of counterexamples. It is an iterative work until all the false counterexamples are cleared. And we find some good deadlock bugs and we verify this setup with where we missed some bug and reproduce it in our this converted flow. So it requires good understanding of the microarchitecture. So amount of time required to come up with the stable safety property converted depends on the understanding of the microarchitecture. So that's how fast we can debug and represent a safety equation. So start with a smaller, choose a smaller value and run formal verification, debug the counterexample, identify the reason. So it gives insight into the failure and why some like anti-starvation, some respin logic is present. So based on that and assumptions, we can update the lifecycle equation, then rerun again until all the false counterexamples are cleared. So it requires some counterexamples will take 1 day or 2 days, but until the formal is running effectively, it is not saturated. So keep on running iteratively until there is no false counterexamples. So then, once the property is running without any counterexamples and the depth is keep on changing, maybe the depth, the safety value is maybe more. So we can reduce it. So in that way, we can improve the proof on the property by converting liveness to safety. It gives more confidence on the setup. So some of the parameters that is used in the safety equation for our interconnect design, like it depends on the number of nodes, because the message travels in a ring format, it goes through all the nodes, and there exists register slices between the nodes, and maximum number of delay. So maximum delay that a respin packet can take or the anti-starvation mechanism can take. So all these parameters comes into the safety equation of the converted property. Also the assumptions, liveness assumptions. So if the liveness assumption proof is directly proportional to the assertion which we are converting, we will see a counterexample where the liveness assumption is not honoring. So we will see that false counterexample. We need to fix the liveness assumptions also into safety. So third method is case split based assume guarantee reasoning. So it is a compositional approach where the proof of the parent property is split into multiple subproofs. And again, those subproof can be split into multiple subproofs. In this way, we can create a structure and prove the main property with the help of helper covers. For example, a property in Interconnect verifies the target end-to-end checker from one source to all the destination. So the message from the source is eventually accepted at the destination for all the destination. So we can be split, this property can be split into one source to one destination or based on the message type. So in this way, using this principle, we can split the property in a hierarchical way and create multiple proofs using the helper covers, helper assertions, and prove them first and use the proven properties across the other proofs. So this is a snapshot of the result. So consider there are like A and G are the two tasks. So the task A proof depends on the proof of task G. So the task G has 10 properties, for example. So we need to prove those 10 properties first, then assume it for proving the property in the task A. Similarly, sublevel 2 and 3. So consider a case, consider a deadlock. So where interconnect is not empty eventually when the sources are not sending any packets. So there is some packet stuck in the design. It may be respinning or stuck in the buffer, and the sources are not sending any newer packet. So that's the bug we missed in the formal flow. So we spent some more time, and finally that bug is reproduced by the special core constraint checker in 32 hours, whereas our formal model end-to-end checker could not reproduce this bug. So this is the problem statement. This is the problem statement why our formal model end-to-end checker could not find this bug. So but the challenge is finding these bugs in the presence of denial of service bugs. It is more challenging because formal gives those bugs first. By the time we reach what we want to recreate, we never know. So how we can reproduce a bug which we want to recreate in the presence of other bugs? So there we used guided bug hunting and written this helper cover. For that case, interconnect is not empty when the sources are idle. Like helper cover, source components are not idle for non-consecutively for 10 cycles, and then source components are idle for 10 cycles. So using this cover, first we have proven this from the state of this this cover. We have run the formal model end-to-end checker and also the non-E2E. So we reproduced the bug with both the checkers. And whereas if you see the formal model end-to-end checker could reproduce the bug 32x faster compared to the unguided bug hunting, and also much more faster than the non-E2E. And also we could reproduce this bug in the presence of other bugs. It is a more good learning from the experiment point of view. So over the year, number of features are added. So we worked on these different methodologies, converting property to safety and case split. We got chance to understand the microarchitecture from the formal perspective. We added good helper covers and helper assertions. So with helper assertions for the latest feature, using the guided bug hunting, we could find 13 bugs. It is like a 2x more bugs than the classic formal. So as you can see, the bug count is also more. The time to hit the bug is also much faster. So with the manual approach, configuring the initial state, because some initial state may be much deeper. So some cover may not converge. So we need to be little bit work on convergent cover if the design activity takes more number of cycles, more depth. So we can reuse those covers. So summarizing the complete presentation, using human and artificial intelligence, we can reproduce interested deadlock bugs. It need not be deadlock bugs, any bugs, using the artificial intelligence, the guided bug hunting, find the real deadlocks. So the investment on the safety, converting property into safety and constructing a flow with the help of invariants, that is the helper assertions, it is a good investment for the long run. So we can add a good number of helper covers and assertions. Our understanding from the formal verification perspective will be very good. So also important factor, managing LSF resources. So these days tools have a machine learning feature. So if tools don't have machine learning feature, right, what we do is, we can do is, depending on the feature update, what properties are not in the COI, we need not to run. So in that way, we can save LSF resources. If there is a machine learning feature, we can enable it and get good benefit of the machine learning feature. So in the subsequent runs. Also, this LSF resource setting is very important for the bug hunting flow or assume guarantee flow or converting safety. If we are not giving the right resources to the tool, then the proof or the property formal verification might not be efficient. We may think we have run for the 24 hours, there is no bug, it's good. But we need to make sure, we need to observe the health of the engines over the like whatever runtime we have set. So with this, all these methods, we can achieve shift-left formal verification. We have achieved in finding more number of bugs in more quicker time. And also the understanding is better as the number of features are getting added to the interconnect. So it is easy to update the setup now. Thank you.
Thanks a lot, Sachin. Very illustrative presentation. Thank you very much. Questions for Sachin?
So Sachin, how do we identify the guide points?
Sorry, cut point.
Guide points from where you want to start to be able to achieve those bugs faster.
Covers, helper covers.
Guide points you talked
Guide
about,
points.
no? Yeah. So how do we identify those guide points?
So, like I mentioned, it requires like understand the target property. Like let's say in interconnect, if a message is sent to the interconnect and eventually accepted, right? It is a complete assertion, but the cover can be the message is seen at the destination. It is some event close to the target assertion proof. So identify the cases which is close to the proof of the target assertion.
So you are basically writing those cover points, right?
Yes.
But how they are assisting the formal engines to find those corner cases
So there
faster?
is, so as part of bug hunting flow, so you can use those cover points as an input. So tool has a bug hunting, so you can use.
Okay, got it.
So you can use it. So now like before.
It's not like you are changing the reset state of the, basically out of reset, your design will still start from the original state, but tool will be using some other bug hunting modes to basically guide.
Yeah, it is a manual guided bug hunting.
Okay.
So there is a lot of experiment going on in EDA on the bug hunting. So we can use the help, like research state is like an initial state for the complete proof, right? So in that way, guided bug hunting where we use the cover state, where the cover is covered, from that point, we can give as an input to the assertions and we can run using the EDA, whatever commands.
Okay, thank you.
So how did you come up with the number for the safety property? Was it a gut feeling that it should be 10,000, 100, or was it something involved behind that?
So I started with some random value. So then I debugged the counterexample. So in that way, like depending on the when I debug the counterexample, I understand why the message is not sunk. The message can be stuck in the skid some buffer. So based on some design functionality, there is some feature which will take out that message after some time. But whatever time I have given, it is less. So in that way, I calculated and increased. So sometimes the message is stuck in the interconnect, rotate, it is respinning. So there is a maximum time, there is anti-starvation logic which will calculate maximum time that message can be in the ring. So based on that, whatever parameters used for the anti-starvation, right, we can calculate the equation for the life cycle of the message.
Let's say it happens that you started with a bigger number directly itself.
Sorry?
Let's say you started with a bigger number itself. And let's say your propagation requires only 20 cycles. Okay, but you thought maybe it's going to be 30, and you started with a 30. Then based on that, even if I'm writing a safety property and I'm saying within 30 cycles it should go out, it's going to hit. Okay, so how are you going to ensure the performance factor into your particular property?
So the verification is eventually the message is accepted, deadlock verification.
Then it's liveness itself. No? I can just write a liveness property and I can say that there is no external dependency, because yes eventually also means within a finite runtime the tool itself is trying to cover that whether you were able to propagate the request itself. Why write 100 or 1000? It should be a fixed number, a hard code fixed number. That if it's 7, it should go out within 7.
Interconnect can be configured into large number of times. So interconnect can be configured into large number of times. So it can be 4 node. So there are multiple number of parameters where the life cycle of the message depends. So we cannot set one particular value. So it is like the flow of message in the interconnect is out of order. So we cannot like set the constant value.
Usually in such scenario, we assume the worst case. So let's say there are 2 cases, 20 case and 40 case. We'll say within 40, but 40 has to come from something, not from the gut.
Your voice is not audible, actually.
So I'm saying that let's say there are 2 cases for the propagation, either it's 20 or 40, and 40 is the worst one. Then we'll say 40 is the one which I cannot say that it should be 50 or 60. So let's say there are multiple cases, and in that multiple case, we come up with the worst case when we are writing the safety property. But anyway, anytime, then that number when it comes to safety, it should be from the calculation, not from the gut. So second question which I have.
Sorry to interject. It's a very good conversation happening. I would request if you can take this offline,
Sure.
Because of the time constraint. We would like to move to the next chain. Maybe Nitin, you can also chat with him separately. Thank you. So we'll go for the next presentation. Thanks, Sachin. Before that, maybe let me request Vichal to present the certificate. In the intervening time, please do not forget to give your rating for each paper.